Greetings everyone, welcome back to calculus. Now we get to start the fun stuff, right? Derivatives, where we really start doing some calculus here, okay? First of all, we need to talk about some geometry. There's a difference between what we call a secant line and a tangent line. A secant line is a line that intersects a shape in two different spots. Okay, typically close to each other, but still very separate. Okay, and a tangent line is a line that intersects a shape just once, but it doesn't just intersect it to cross over it. A tangent line is meant to just skip off of the surface of something, right? So when you see a tangent line go across something like this, you'll know it's a tangent line because it stays on the same side of the curve on both sides of the intersecting point. So by tangent something, we mean just grazing it, right? Just scraping one point off of the surface of it, right? So a tangent line can rotate to different points along the surface there, okay? So a secant line is meant to give you an idea of just a general trend of a graph over some interval, right? So the interval between 2 points can be sort of an average trend. Hey, where does this thing look like it might be going? And depending on how big of an interval, you may have a really good average, or you may have a really bad average, or you may have a good idea of where it's going or a bad idea of where it's going. So that's the problem with secant lines. It's an average, okay? If you take a slope from the 2 points that a secant line hits a function, you get what we call the average rate of change over that interval of the function, okay? It's an average because it's over some distance of an interval, a beginning and an end. So flip to the other one, tangent lines are the opposite, okay? You can still think of this as a trend of which way a function is going, which way a function is changing, because a tangent line is basically pointing the same way that the function is at an individual point, right? So there's a word in here that I need to point out, okay? Local to a point, okay? A tangent line may intersect a function somewhere else, right? So in other words, if I keep drawing this tangent line out this way, it looks kind of like the function might actually intersect it again. That's okay. A tangent line is tangent to a graph locally. We're only interested in this little section right here. And if you look really closely there, you'll see it looks like the line and the curve are practically the same thing for a real small little distance right here. A really, really tiny piece of it looks like you can almost not even separate them from each other. They look almost identical locally on a small region, okay? And that's the idea you should be getting from a tangent line. It's almost like being able to take a very small piece of the function graph itself and say, look, here it is, right? So being able to find a tangent line or the slope of the tangent line is an important measurement that we do in calculus. So important that we actually gave it a name, right? That's where the word derivative comes in. We're going to be deriving small pieces of functions by using slopes of tangent lines, okay? So a secant line slope is an average measurement of the change, okay? The tangent line slope, not the line itself, just the slope measurement of the line, is going to be an instantaneous rate of change, okay? An instantaneous measurement of change at that point, okay? So let me see if I can give you a realistic idea of this. Imagine you're taking a long trip in your car, right? So like an hour-long trip from here to a different city, right? You have little small roads that you have to get out of your house from first, and you have a few stop signs here and there, and then eventually you hit the interstate, right? And then you go a certain higher speed for a while, and then when you get to the city of the place you want to go to, you have a few other small streets with stop signs and stuff. So if it takes you an hour to get there, right, and in that hour you traveled, I don't know, 50 miles, right? Let's say from one destination to the other, you traveled a total of 50 miles in that 1 hour. Well, then someone might say, oh, well, you went 50 miles an hour. And they'd be sort of right, but think about it. That hour was like a long interval, and it had a beginning and an end. And it's like they're trying to do one measurement as an average for the whole trip. That's what a secant line is doing. Did you go 50 miles an hour the entire time on that trip to the other city? Well, hopefully not. Hopefully you weren't doing 50 miles an hour through a stop sign, I hope. And hopefully you weren't only doing 50 miles an hour on the interstate, right? Speed limit's 70, you should be doing that. So that's why it's like an average when you do a secant. All you're worried about is where did it start and where did it end, and it's a total change over the whole thing. That's a secant slope. Whereas a tangent line, an instantaneous slope, would be while you're driving that trip, every now and then you look down at your speedometer to make sure you're not going over the speed limit, right? So maybe you're going down one of the little small roads and you measure 37 miles an hour on one road, and then at another time when you're on the interstate you measure 75 miles an hour because you're passing somebody on the interstate, right? Or something like that. Okay, that's instantaneous. I'm looking at one measurement for that one moment, at each moment of my journey. Okay, so that's the difference between a secant line slope and a tangent line slope here. Okay, the slope that you would get from this covers an entire interval, and it's an average. Okay, so it's like a generic feeling. This is something that you might do in algebra, and we'll do a couple here, but we're more interested in this. The tangent line problem for us is that we're interested in being able to measure little speeds, little changes at each moment of a function. At each point of a function, I want to measure a little change at that point. And that's where the beginning and the basis of our calculus comes from, being able to pick apart these little changes at every single point that we're interested in. Okay, so we'll be doing slopes of tangent lines, and sometimes we may even calculate the entire equation of the whole tangent line, but you still have to start with a slope to do that. Okay, so we'll be doing calculations of slopes of tangent lines, and the name of that action is taking the derivative, right? The derivative is a word meaning the instantaneous rate of change, or it can also imply the slope of a tangent line. Okay, that's what derivative is going to imply. Instantaneous rate of change is derivative, and slope of a tangent line is the derivative also. Okay? All right, so let's look at some of the formulas that come from this. Average rate of change. Okay, this should look very familiar to you. Okay, even if you haven't done a lot with this particular formula. This is your typical slope formula from any algebra class. Remember, function values are y values, right? So this is just y minus y, right? Delta y. X minus x, delta x. That's just rise over run. Good old slope, right? Of some line. But since it's two different x values, x and a here, then I'm actually doing an average rate of change, right? It's a secant line, if you will. Another way of doing an average rate of change is called the difference quotient, and it's basically the same thing. It's still the subtraction of two function values, but it's just rewritten so that the denominator is simpler, right? Instead of having the denominator as a subtraction, the denominator is given a name, h, or you could even use delta x there. Some people do. I'm using h because it's less confusing to write one letter when you're putting things into a formula. Okay, so h is basically the run of my slope. So if I pick a value x, then to get to the next x is just that x plus the h. So that's where these two function values come in, right? These two y values here and here are just the function at that further x, x plus h, and minus the current one, right, x. So both of these are the same thing. They're slopes of a secant line, which are average measures of change. Okay? So that's what we want to upgrade now. We're going to upgrade our average rates of change to instantaneous rates of change, or in other words, the derivative. And we do that with limits. So watch, here's what actually happens. What I'm going to be doing to let this first version right here, I'm taking this average rate of change formula and I'm converting it with a limit. The limit as x approaches a. So in other words, if I let x move this way towards a. So a is a number that I'm interested in, obviously. A is some x value that I'm interested in. And I'm going to take whatever x values are on this side of it, let's say. And by the way, it doesn't have to be this side. It could also be this side. Remember, limits come from both directions. So technically, I could also be picking a point on this side. This is just the graphical representation I have at this moment to help you out. But if I let x approach a, right, notice what happens is this point will move along the curve. And remember, limits are all about asking everybody right up to it, right? And most of the time, remember, we can calculate the limits either the stage 1 easy way by plugging something in, or stage 2 by simplifying something. I want to point out right now, this can't be done by stage 1, because if you plug in a for x, a minus a is 0 in the denominator, right? So already you should be feeling like, oh, this is where a lot of those stage 2 limits come from. You'd be right. Whenever we set up a lot of these limits, you're going to find that they're limits that I can simplify first while the limit is sort of playing that delay game, and then I can plug in later. Okay? So for my limit, like I said, I'm letting x approach a here. So this point would approach this point. And notice as it's doing that, right? I'll use this as my line here, right? As x approaches a, you'll notice that what happens is that line will slowly start to do this. It'll start to become a tangent line like this. And if x actually does land right on top of a, boom, you have a tangent line, and this is what happens. Okay? Right here would be the point that we're interested in at a. Okay? Same idea with difference quotient version, okay? It can still be a derivative also by inputting a limit. But again, it's about letting the points come together. So in the difference quotient version, I have labeled the run as h. So what I want to do is let h go to 0. And this is actually the derivative setup that we use a lot more. This first one is useful on a couple of different proofs, but this version is really nice and easy to use when we're doing individual derivatives because it's easy to simplify out an h. If you've ever done difference quotient in college algebra or anything like that, you'll probably recognize how we always simplify something out in order to get rid of that h in the denominator. Now you're going to get to understand why, because notice I can't just plug in 0 for h. Not yet, right? That would be a division by 0. But after you set up your derivative, then probably what you can do is simplify it some kind of way, right? And then the limit is playing a delay game. Okay, after that gets simplified and you get rid of that h in the bottom, then I can plug in the 0. Okay? So that's what's going to end up happening. But notice it's the same idea as before. If I let h go to 0, this is going to get smaller and smaller, and this point is going to approach that point. Again, it could have been from the other side. I could have defined h to a point on the left-hand side. So this limit is valid from both sides. Okay? Since we're using limits of a function, okay, since we're using the limits of the function, and one more thing, the point has to actually exist on the function, or else taking the derivative there doesn't make sense, because I can't change something that doesn't actually exist at that point, okay? So what I want you to realize is, since I'm using a limit of all these values to approach this point that I'm interested in, and the function value has to exist there to have this tangent line, taking a derivative implies continuity. And vice versa. If you've already proven continuity, then it implies that you can take the derivative. Okay? So what we say is being differentiable at a point if and only if you are continuous at a point. In other words, they imply each other. So if I can take a derivative, if I can do a slope of a tangent line at a point, then it's continuous at the point. If it's continuous at a point, I can also take a derivative at that point, or find a slope of a tangent line at that point. Okay? So they go hand in hand, continuity and derivatives. All right? You can't have one without the other. They imply each other. Okay? All right, so keep these formulas in mind. That's what we'll be using to do some of our calculations. Time to put our math where our mouth is. Let's calculate some slopes here under those different headings. We're going to calculate the average rate of change on two different intervals, leading up to an instantaneous rate of change on one of the endpoints of those intervals. Okay, so here's my function, 6x minus x squared, and I have a rough graph for you right here. Of course, it's a downward facing parabola, and if you'll notice, what I've done is I've drawn the secant lines that correspond to these two intervals, right? That's from here to here, and then the 1 to 2 is from here to here. And then I also drew the tangent line for the instantaneous rate of change. That's this one here. Okay, so as you can see, the slopes are all similar as it leads up to it, because the interval's kind of small on these. All right, but just imagine if I had picked a larger interval, right? If my secant line was going between the two symmetric halves of the parabola, that may not even be a good representation of what's going on in your graph, right? Because it's like cutting across whole sections of it. This is why we want to work towards a tangent line. We can talk about a rate of change at a single point. We can digest data about a single location on the graph. Okay, so let's do a few of these calculations. If I want to calculate the average rate of change, by the way, this is also a way of calculating average velocity. You might see that one, right? Velocity is distance over time. It's the same thing, rise over run. All right, so first I'm going to calculate a few of these function values to get the y values of the points, right? So f of 3 is going to be 9, right? That's the vertex. We already calculated that one. And then f of 2 is 12 minus 4, which is 8. And then f of 1 is going to be 6 minus 1, which is 5. Okay? So then, to do the calculation here, on the interval from 1 to 3, I will do f of 3, which is 9, minus f of 1, which is 5, over 3 minus 1, right? Because I'm doing x equals 3 for that first interval here. Okay, so I'm getting 4 over 2, which is 2. So that's the slope of this secant line here, a slope of 2. All right, so it just means on average across the interval from 1 to 3, we have a change of 2 on average, right? Let's do the same thing between 1 and 2. That would be the slope of this line right here. So that's going to be f of 2 minus f of 1 over 2 minus 1. So I'm getting 3 over 1, which is 3. Okay? And See how that makes sense? The more I've moved this point this way, look, the slope did get steeper, right? So we can expect the slope of this tangent line to be even yet steeper than those two, right? Let's actually perform this limit. Right here, I have the limit as x approaches 1 of 6x minus x squared minus f of 1 is 5 over x minus 1. Okay, let's rearrange these terms a little bit. So I've got limit as x approaches 1. I'll put my negative x squared in the front, and then I'll have plus 6x minus 5 over x minus 1. Okay, so I need to perform this limit. If I try stage 1, plug in the 1, division by 0. Let's see if it'll work with the stage 2 though, right? Plug 1 into the numerator. All right, so negative 1 squared plus 6 minus 5 also gives me 0. So I have 0 over 0, which means, oh, I'm in good shape. That just means I need to use a delay tactic, right? Stage 2. Let the limit just sit there for a minute while I simplify this. Then I can try plugging it in again. Okay? So by simplifying, of course, we mean let's factor what we can and see if anything will eliminate. Okay, so I have limit as x approaches 1. And then I need to factor this. I'll have negative x and x. My denominator hasn't changed, x minus 1. Let's see, that would have to be a 5 and a 1, right? And then it would have to be a negative 1 and a plus 5, right? Double check, negative 5 plus 5 plus 1 is 6, yep, and then negative x squared, good. And it works out, look, the x minus 1s can eliminate, leaving me with the limit as x approaches 1 of negative x plus 5. Well, that's just negative 1 plus 5, or in other words, 4. So that's the slope of the line that is tangent at that point. By taking this limit as I let x get all the way close to 1, I have actually been able to calculate the slope of a line that I only know a single point for, because I know it has to brush along the edge of this curve. I only need to know the single point of tangency to let my limit approach it. And therefore, my instantaneous rate of change at x equals 1 of this function f is 4. Another way to say that, the derivative of f at x equals 1 is 4. Okay? Several different ways that you can go along with the meaning of that, because we have instantaneous rate of change, slope of tangent line, and derivative. All three of those mean the same thing, and the wording you can use all different kinds of ways depending on the application you're doing. Okay? Look at this next one that I have here. Find the equation this time of the line that is tangent to g at x equals 4. Here's my g function. Here's the graph of g in blue. And then look, that's the tangent line that we're trying to find the equation of right there. Think back to all of your algebra days. How do I make the equation of a line? What's the easiest way to do that? Point slope formula, right? I need to do something like y minus y naught equals m times x minus x naught, where the y naught and the x naught is some point, right? Why not? Use a point that we already have. Why not? Right? Okay. I've already got my x naught. That's the 4, right? How do I find the y value? Well, I can plug that in and find that, right? I need to find g of 4 anyway. What's g of 4? 1 over 4 plus 1. That's 1/5. So look, as far as making the equation of a line, I've already gotten 2 pieces of information. I have an x value location and a y value of the location of the point. So I already have this much. Y minus 1/5 is equal to something times x minus 4. But this is the something that's the key here. This is the something that really is what this section is all about. We could do points all day long in algebra, but finding the slope of a line that is tangent, that's where we're crossing over into our calculus zone, right? This is where we need to start talking about slope of a tangent line, instantaneous rate of change, derivative, whichever one you want to call it. That's what we need here. I need a slope, so I will be taking the derivative here. Let's use the same setup that we have over here. I had the limit as x approaches a, whatever your point of interest is, f of x minus f of a over x minus a. Let's do that. So I've got the limit as x approaches 4, right? That's going to be from both sides, okay? Because I could have points approaching it this way. I could have points approaching it that way. This function is completely continuous everywhere except -1. So we're all good at 4, right? So limit as x approaches 4 of my f of x, right? That's 1 over x plus 1 minus f of a, or in this case g of a, g of 4 is 1/5 divided by x minus a, or in other words, x minus 4. Okay? Now I want you to think back for a second. This limit should look familiar. Several lectures ago, when we were talking about limits, we did this one a couple of different ways, right? This is one of those ones that we've already done. Let's go ahead and go through it again real quick. I realize that once I plug in the 4, that I'm going to get 0 over 0, something I can simplify. So I do that by multiplying the LCD all over the place here. That means I'm going to multiply by 5 and x plus 1, 5 and x plus 1, and put some parentheses here, 5 and x plus 1. Okay. And we're calculating our slope here. So I'll go ahead and put an m there for this one. Okay, so what is this equal to? I've got the limit still. It's doing this little delay a game, right? It's holding back, waiting for this thing to get simplified so I can plug in the 4. The x plus 1s eliminate. The 5s reduce. So I'm left with 5 minus x minus 1. Be careful there because this negative distributes to the x plus 1. And in the bottom, I'm left with x minus 4 times 5 times x plus 1. I've got 5 minus 1 in the top here. So I have 4 minus x over x minus 4 times 5 times x plus 1. Alrighty. Remember, these can reduce 4 minus x and x minus 4, but they're opposites, so that leaves behind a -1. Now it's safe. I can plug in the 4 because I got rid of the piece that is bad for it. I have -1 over 5 times x plus 1. And if I plug in 4, I've got 4 plus 1, which is 5, times the 5 is 25 in the bottom. Okay, so altogether I'm getting -1 over 25 is my instantaneous rate of change. Notice how it makes sense. This is not a very steep line, but it is decreasing, right? The slope is negative. So I'm going to take that slope and I'm going to put it into this equation so that I can finish it up. I have y minus 1/5 equal to -1 over 25 x minus 4. I'm going to distribute the slope. So plus 4 over 25. And I really probably want this in slope-intercept form. I know it didn't say at the beginning. Typically, we want these in slope-intercept form so that we can talk about their slopes and have them in a function format and things like that. I'm going to add 1/5 to both sides here. But instead of writing 1/5 here, I'm going to write 5/25. Notice that's the same thing as adding 1/5. But here I just needed to add it to eliminate those. Here I'm adding, and I need a common denominator to combine, right? So let's see, I am left with y equals negative 1 over 25x plus 9 over 25. Okay? Now I know this isn't the best representation. I'm just giving you sort of a hand-waving graph here. So in just a minute, I'll show you what this really looks like in GeoGebra. Okay? Some high points. Don't forget again, the slope was negative. And notice it does actually look like it hits the y-axis pretty low because the y-intercept here is actually 1. So it's a lot lower than 1 where it's intersecting there, right? And 9/25 is the actual point, okay? So a lot of the algebra here is no different than what you've seen before. The only twist is where am I getting my slopes from? And this is what we'll be doing for quite a while, finding derivatives, calculating slopes of tangent lines, finding instantaneous rates of change. All three of those mean the same thing, and it means doing some sort of limit as x approaches a certain point. Okay? It also could mean letting your h go to 0 if you do the other format. Okay? So go take a look at the GeoGebra on this one, and then let's do some more examples. First, let's take a look at the parabola that we graphed and did the rates of change on. 6x minus x squared. There's the graph of it. And remember, our point of interest was at x equals 1. And then I also had these other 2 points to do average rates of change with. So notice here's the secant line between the x equals 1 and the x equals 3 point, right? This is a secant line, and you can tell the slope here, right? Up 2 over 1, right here. Then, of course, we can switch to these, the secant between these 2 points. And if you compare the two, you'll notice, like, as the point moves along, you can see the line does get steeper, right? And here the slope is 3 over 1. And then, of course, the tangent line is even steeper than the other one. You can tell if I go up 1, 2, 3, 4, and then over 1. It definitely has a slope of 4. And the thing to notice is right here, local to the point where we're interested in, right here where x equals 1, you'll notice for a good stretch of it, you really can't tell the difference. Here, let me zoom in. You can see. See, even as close as I get, there's a stretch here in the middle, just local to the point, where you cannot tell the difference between the tangent line and the graph itself. Okay? That's one of the reasons we liked to find tangent lines, to approximate curves. It also shows the same direction that the graph is changing. Right? You can use it to sort of mimic the graph there, if you will. Okay, and the other one that we discussed was this graph right here. Y equals 1 over x plus 1. Has the vertical asymptote at -1 here. And the point we were interested in was x equals 4. And we calculated the tangent line to be this -1 over 25x plus 9 over 25. And sure enough, there it is, right? That is the equation, that is the line that is tangent to the graph just at that one point, though. If I move my point even a little bit, the tangent line would change, right? It would slant in a different direction.
And just like the last one, notice at this little region local to the point, because that's really where we're interested in the tangent line. We don't really care about all of these other points on the tangent line way over here. But local to the point here, you can tell that the function and the line are not distinguishable.
Next, I want to talk about how to upgrade our workload into something slightly more efficient. So far, we've been calculating all of our slopes individually, okay? Like what we're doing here in just a moment. And what I want to show you is there's actually going to be a more efficient way if you want to take the derivative at several different locations of a single function, which is going to happen a lot in the things that we do because we evaluate functions at all different points, okay? So here's an example. Let's do a couple of these, okay? This time I'm using the other definition so that we can get a few examples of both. All right, so it's using difference quotient version. I want to calculate the derivatives of this function at both x equals 1 and x equals 3. Okay? So here I've already got it set up for you right here. And I'm using this notation. I don't know if you go back to that first scene, if you caught on, or if you just noticed it, really is what I should say. Instead of delta y and delta x, remember when it's a derivative, we use the d, right? It's meaning it's a very, very infinitesimally small amount is what we typically think of when we do the d instead of the delta, okay? And it's just another symbol for derivative. So I've got it set up. It's f of 1 plus h, right? F of 1, because that's where my x value, my a value was in the formula that we had on the front screen, right? This is where a was in the other format. And I want to simplify this limit. So I have limit as h goes to 0, f of 1 plus h, that's just square root 1 plus h, minus f of 1 is the square root of 1, which is just 1, all over h. Okay? Now we've simplified a limit like this before. Notice right now I can't plug in the 0 like I want to. We're going to do that little delay tactic. But remember, the way we handle limits with these radicals like this is we multiply by conjugates. So I'm going to multiply this numerator by his conjugate. That would be square root of 1 plus h, and then plus 1 on the outside. And then, of course, to make that legal, I'll have to do the same thing in the denominator. Okay, so when I multiply this out in the numerator, I'll have limit as h goes to 0 of 1 plus h, because the square root times itself gives me, right, that same thing back again. Then I'll have my cross terms, which is just going to be 1 times the radical, so it's plus square root of 1 plus h, minus square root of 1 plus h again, because of the inside multiplication here. And then lastly, negative 1 times 1 is minus 1. And I'm not multiplying out the denominator. Like so. Okay? So then notice here, I get some things eliminating, right? Like we wanted. These two are going to add to 0. Negative 1 plus 1 also adds to 0. And then with all of those things gone, I'm left with h divided by h. Okay? So then here's what I have left. I have the limit as h goes to 0 of 1 over square root of 1 plus h plus 1. Okay, so remember the h over h just reduced to the 1 that you see here. And now it's okay to let h go to 0. So I plug in 0 for h, it's not going to cause any division by 0 or anything. What I'll get is just the square root of 1, right, which is 1, plus the other 1. So I'm getting 1/2 here. Okay? So that's my instantaneous rate of change at x equals 1 on the function square root of x. Okay? It also asked us to do the same thing at x equals 3. So we start back all over again. Here's the definition of the limit, right? Instead of 1 being my a, now 3 is my a. So I set it up very similarly. I'll have limit h goes to 0 of square root 3 plus h minus square root of 3 all over h. Just like before, I'm going to multiply by his conjugate, just like I did up there. All right. So limit as h goes to 0, and his conjugate is the square root of 3 plus h plus square root of 3. That's what I'm multiplying to the top and bottom there. But when I multiply the conjugate to the top, remember the radical portions are going to cross out immediately. And what I'm left with is 3 plus h and minus 3. Let's go through that again real quick. If I multiply by his conjugate, the cross terms are going to be those radicals that wipe out. And a square root of 3 plus h times a square root of 3 plus h gives me 3 plus h. And a square root of 3 times a square root of 3 gives me a 3. But in this case, one of them's negative, the other's positive. So I get the negative. Immediately the 3's will add out. And I'll have h over h, which reduces to 1. And I have square root of 3 plus h plus square root of 3. And it's completely safe now to plug in the 0 for h. So I get 1 over 2 square root of 3. Whatever that number happens to be is my derivative, my instantaneous rate of change, my slope of a tangent line at x equals 3 on the function square root of x. And we could sit here and keep grinding these out over and over and over again. I'm trying to make a point here. It's a lot of work just to get one of these derivatives to crank out, right? And I'm doing it to the same function. It's going to be the same process over and over again. Why are we doing this to individual numbers? The whole concept of functions was designed so that if I set up an input process, it does something and then has an output after that process, right? Well, there's no reason why I couldn't do this to a derivative also, okay? So this is the upgrade that I was alluding to earlier. We're going to start calling it the derivative function. Okay? Not to be confused with your actual function. I will be taking the derivative, but I won't pick an actual x number first. I will just say I'm taking the derivative. And what that means is I'm going to leave the number portion here as an x. Instead of picking an a value to put in for x, I'm literally just going to put the letter x there and then simplify it generically. And what will happen is I will then have a formula with x's in it after the limit is computed, right? Because after the limit is done, all the h's are gone. I'll be left with something with just x's in it. And then I can pick whatever x I want. Okay? So, the way we talk about derivatives when they're slopes, we write dy over dx. When I want to talk about the derivative as a function, I also have another option. I can write it as f prime of x, like this. If there's a little tick mark in between the function name and the parentheses, that means I'm taking a derivative. This is a derivative function. So it's not the same as the original function. It is the derivative function. Okay? An original function f, when I plug in an x, it gives me y values. A derivative function, if I plug in an x, returns slope values at each point. Right? That's what derivatives are. Instantaneous rates of change, slopes of tangent lines. If I create a derivative function, you input x's, it outputs slope values, rates of change at those x values. Okay, so I define it the same way. I still use limit as h goes to 0. I could also use the other definition, by the way, and on occasion we'll switch back and forth. Typically, this is the one that gets used more often with this, just because it's easier limits to simplify. Okay, so now let me do this same derivative one more time, but we're going to do it generically to just some x value that hasn't been named yet. We'll create a derivative function, and then I'll test it on these 2 points. Okay, so f prime of x is now equal to limit as h goes to 0, f of x plus h. Here's my function, so that's going to be square root x plus h minus the original f of x, which is square root of x, all over h, like this. Now I can't plug in 0 for h yet, right? Division by 0 problem. But I'm going to simplify it the same way we've been doing these. I'm going to multiply by a conjugate, and I'm going to simplify these limits so I can plug in my h later. So I'm going to multiply by square root x plus h plus square root of x. And I'm going to do that in the numerator and denominator, like so. The result I have x plus h from this multiplication. I've got minus square root of x times square root of x plus h. That's this multiplication. I've got plus square root of x times square root of x plus h. That's this multiplication. And I have minus x. That's from the last multiplication. All over. The denominator is unchanged, like so. Alrighty. I notice right away that this and this will add to 0, and also that my x minus x will add to 0. Nothing is left in the numerator except for h, and then I can do h divided by h, which will be 1. Okay, so my derivative function f prime of x has now been reduced to the limit as h goes to 0 of 1 over square root of x plus h plus square root of x. It is now safe to plug in the 0, right? When I do that, I'll have square root of x plus square root of x. So that's 1 over 2 square root of x. So notice what I have here is a function. It's not the same as the original f function. It is a different function. But I can take this derivative function, feed it an x value, and it will then give me the slope at whatever x I feed it. So they could have asked for 2 different values. They could have asked for 20 different values. Or let's think of it in terms of future uses, right? This is a way that we look at individual points and how their slopes, how their rates of change are at each point. When we look at functions, we look at multiple points. I'm going to want the slope at several different points, right? That's what the point of this is getting at here. I'm not going to do individual derivatives like this anymore. Every time we need a slope of something, my first go-to is going to be, let's find the derivative, right? Which implies a derivative function. I will do it generically, and it will be something where if I plug in an x value, I can then be given out a slope at that x value, okay? Here, notice, where x is 1, if I plug in 1, square root of 1 is 1 times 2 is 2, I would get 1/2. If x is 3, Notice I would have 1 over 2 times square root of 3, which is exactly what I have over here. Okay? But the way I've done it here, I could ask you 20 more x values and you just plug in the x value, crank out a bunch of slopes. Okay? So this is the way we will be doing our derivatives from now on. I will find a derivative function and then plug in whatever x values I want later. Let's get a little more practice finding the derivative function of a function, right? So if you ever see find the derivative, right, and they don't give you an x value, they mean they want the derivative function, okay? Now, of course, you've already seen me use dy over dx. And in the last scene, I also used f prime of x. You could also use things like y prime. That's acceptable. And sometimes on rare occasions, some people also use something like this. They'll use big, bold letter D and stuff like that as an operator, if you will, right? So any one of these symbols can be used for derivative. Although typically we use one of these two, and then sometimes maybe even the y prime. We won't do too much of the official things of these things. Okay? All right, so when I'm doing a derivative function, I typically use f prime of x. And the reason why is because it gives me that input spot so I can keep track of what I'm actually calculating and where is it supposed to be applied. All right, so f prime of x is equal to the limit as h goes to 0 of the f of x plus h. So that's going to be x plus h to the 4th plus 3 times x plus h minus 7. That's f of x plus h minus the original f of x all over h. Okay? So the only thing in here that's even a little bit beefy is this x plus h to the 4th. Okay? Now, of course, one way that you could do this is you could write out all of this like this. Okay? And of course, the most efficient way to do it is to multiply your x plus h's here and here, and then also multiply these two here and here, so that you have two of the same thing. So that would be x squared plus 2xh plus h squared, x squared plus 2xh plus h squared. And then from here, you would want to multiply those out. I would obviously have x to the 4th. I would have 2x cubed h. I would also have x squared h squared. 2xh and x squared would be another 2x cubed h. 2xh times 2xh would be 4x squared h squared. And 2xh plus h squared would be 2xh cubed. Okay, then going through the last one, x squared h squared is this first one, right? Then 2xh cubed and h to the 4th, which I would then sum all of that up into x to the 4th plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the 4th. Okay, so a yummy multiplication there, polynomial stuff. As an intro here, I want to show you another way to multiply that that could possibly save you time, especially if you were doing something even higher than that, right? 4 wasn't too bad, but imagine if you were doing 10 or 15 or something like that. Wouldn't it be great if there were a way that you could just go straight to the result? Okay? Well, I want you to notice the pattern first in the multiplications, right? Do you notice it goes x to the 4, x to the 3, x to the 2, x to the 1, and no x's, right? So 4, 3, 2, 1, none for the x's. And then the h's is exactly the opposite. None, 1, 2, 3, 4. That's not a coincidence. Anytime you're multiplying two objects, but those same, I'm sorry, not two objects, but you're multiplying a binomial times itself, okay, it's always going to do that. Notice when I just did two of them, right? See, x is 2, 1, and none, and then h is none, 1, and 2, right? It does that no matter how many times you multiply it. H will count up, x will count down as the terms go, okay? So the only other thing missing then is, what if I want to multiply this out? Where do I get these numbers from? Okay, well, we have something called Pascal's triangle. Pascal's triangle is easy to remember. You start with a 1 and then put in the next row down, it'll be a next, it goes by rows here. You still put some 1s, and then every time you want to start a new row, you start and finish with a 1, and any number that's in between, you add. 1 plus 1 is 2. So I start with 1, 1 plus 2 is 3, 2 plus 1 is 3, finish with 1. Start with 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, finish with a 1. Now look at this row. Right? 1, 4, 6, 4, 1. Not a coincidence. For example, let's say I want to know what x plus h to the 6th is without having to go through all of this. Easy. I'll just do 2 more rows here. And the way you know you're at the right row is the second number in the row should be the same as the exponent. So I know this is the 6th power row right here. Okay? And then I just remember that my x's have to count down in power and my h's have to count up. And it doesn't have to be x's and h's, by the way. This could be any two objects. Any two objects. And it would work the same. So x plus h to the 6th is going to be 1 x to the 6th. Now start counting down with your x's and up with your h's, right? 6 x5h, 15 x4h squared, 20 x3h3, 15 x squared h4, 6x h to the 5th, and lastly 1 h to the 6th. Would be just like that. Okay, so Pascal's triangle and counting your exponents in the correct order, okay, is a quick way to multiply a binomial. All right. In fact, there is a theorem behind this much grander and bigger than for bigger things than this, called the binomial theorem. And it's an easy way to write out these kinds of things. Okay, things that start as a binomial and it uses an exponent. The one we're interested in, though, is this one right here, because I have x plus h to the 4th. So here we go. Limit as h goes to 0. I've got x to the 4th, 4x3h, 6x squared h squared, 4xh cubed, plus h to the 4th. That was just this piece. Plus, I've got 3x and 3h. Minus 7. Distribute your negative. Minus x to the 4th, minus 3x plus 7. And then everything is divided by h. Okay? So remember, my original function should wipe out. So negative x to the fourth, positive x to the fourth, plus 3x, minus 7, and plus 7. Okay? Notice everything that remains has an h in it, and I'm dividing by h. So I'm going to distribute, and I'm going to have h over h squared over h cubed over h. Basically, everything is going to lose an h by division. Okay? So this is what I'm left with. The limit as h goes to 0 of 4x to the 3 plus 6x squared h plus 4x h squared plus h cubed plus 3, and that was the last one. And they all divided by h. That's why they're all missing an h, right? Now it's safe. Let h go to 0. This piece right here is going to go to 0. This piece right here is going to go to 0. This piece right here is going to go to 0. I'm left with 4x cubed plus 3. So my derivative function is 4x cubed plus 3. Okay? And then, whatever points I'm interested in finding a slope at, I can definitely plug in and find those. One more thing I want to talk about before we finish this lecture up is where the derivative can fail or will fail in measurement. Okay, and the three big ones are discontinuities. You kind of already alluded to that one at the beginning. Remember, being differentiable implies being continuous and vice versa, right? Cusps, which are any kind of sharp point or corner on a function, is a cusp. All of the functions that we measure derivatives on are not just continuous, but they're also what we call smooth, okay? And a cusp is the point that we're trying to avoid. A cusp is not smooth. It's sharp, right? Like an absolute value is a V shape with a sharp corner on it. Or x to the 2/3 power has a shape similar to this, right? It's a sharp cusp pointing down like that x to the 2/3 power is. Okay? And then lastly, vertical tangents. Now, vertical tangents aren't necessarily a total failure on the part of the derivative, but remember, any vertical line has a slope which is undefined, right? And we can get a little bit more finely tuned answer for there because we have better language now. Basically, their slopes are a limit leading to infinity, an infinite answer, right? We can't say that the slope is infinity because that doesn't make sense. Remember, we don't use infinity as a numerical answer, but I can use infinity as an answer to a limit. And what's basically happening here is I'll be doing the limit for my derivative, and we will get infinite answers to our limits, right? That means that the patterns go on forever in unbounded ways. Okay, so that's really what's happening with vertical tangents. You can actually have a graph where for one brief moment the tangent line turns vertical, and then it will just rotate another way. So what we say is the derivative is undefined there. Okay, you can maybe catch some people off sometimes by saying the derivative is infinite, but remember, we kind of don't want to use infinity as a physical answer to a function. Right? Infinity can't be used as that kind of answer. I can say that the limit is infinite, right? But the derivative, we say, is undefined. Okay? So 3 different points. Here are some examples. Imagine if I have some sort of piecewise function, right? And this could go bad a couple of different ways, right? The most blatant is they're completely broken, like these are, right? When x equals 1 on this one, it goes up to 4. When x equals 1 on this one, it goes down to -1. And technically the -1 is actually the function value. But they're completely broken. And remember, what the derivative is supposed to be doing is measuring the slope of the tangent line to the function at the point. Well, there is no one tangent line from both directions, right? From one direction you have a tangent line, and from another direction you have a completely different tangent line. So my limit, in this case, the limit blatantly won't even work from both sides. Because if I do the limit from the left, set up my derivative, right? F of x plus h minus f of x over h. But if I do that limit from the left, I have to use this as my f of x. But if I do my limit from the right, I have to use a completely different f of x. Okay? Now, of course, one could argue, well, what if both of them were lines with the same slope? Couldn't the limit be the same on both sides? Sure. But you still have the problem of, even if they have the same slope, they're separated. So they physically have different tangent lines. So which one is the tangent line? Think of it that way is the best way. If it's discontinuous, we can't define a derivative there. Okay? The discontinuity throws the derivative idea right out. And here's another example of that right here. 1 over x squared, the volcano function, right? If I do the derivative when x is equal to 0, the function itself isn't even defined at 0. Not to mention, it's infinite in there, right? So we would say that that's undefined. Sure, if you took your limits from both sides, you could probably argue some sort of infinite answer, but bottom line, there's no function value at 0 to draw a tangent to. So there can't be a derivative either. There's no value to cross over. Okay? Now, what about a cusp? Absolute value of x is a V shape with a 90-degree angle right corner, right in the middle of it at 0. So then what's the derivative of this function at 0? Well, let's set it up and see, right? Let's do the limit as x goes to 0. I'm doing the x and a version, right? As x goes to a, of absolute value of x minus absolute value of a, which in this case is 0, over x minus 0. Okay, so what's happening here is I can do this absolute value is 0, and this is also 0. So I'm getting the limit as x approaches 0 of absolute value of x over x. And of course, it's going to be undefined. You've got this division by 0 going on, but remember, we try to always, simplify the things as best as we can. Absolute value is defined differently from the left and from the right. Basically, what happens is, if I try to take from the left, x approaches 0 from the left, the absolute value of x over x, then I'm going to get negative x over x as x is approaching 0, and I'm going to get negative 1. That should make sense to you. Look, the left side has a slope of negative 1. What's the slope on the right side? Positive 1, right? So here's the problem here. The function is completely continuous. It's all connected, but it's not smooth. In other words, the slope changes too quickly to be measured, right? It just jumps from negative 1 to 1. The slope does, right? This is the slope from the left. This is the slope from the right. It changes too quick. A cusp being sharp, a sharp point, I can't measure a derivative at. All right? We want our curves to be smooth and continuous to be differentiable. To have a derivative is what differentiable means, right? So again, g prime of 0 is undefined. Okay? You're going to run into a similar issue here with this one. If I try to do a prime of 0, which is right here at that vertical tangent point, okay, I'll do the same kind of is up there. I've got the limit as x goes to 0 of x to the 3/5 minus 0 to the 3/5 over x minus 0. Again, these are both 0. So I've got the limit as x approaches 0 of x to the 3/5 divided by x. I can reduce that. The limit as x approaches 0 of 1 over x to the 2/5 power. All right? Think about that for a second. That's 3/5 minus 1, because I just subtract exponents when I divide, right? Because they're both x. I get negative 2/5 from that. So that's 1 over x to the 2/5. Okay, it's a 2 power, which tells you that it's going to act very similar to this volcano function. Not the function itself. I'm talking about this limit. This derivative is going to act kind of like that volcano function. But it's still a difficulty. Can I plug 0 into this? Have I gotten rid of the division by 0 difficulty? No. Remember, this kind of limit is dictated by a vertical asymptote. The original function doesn't have a vertical asymptote, but the derivative does. See, right here, the derivative is undefined at 0. Now, you could argue, well, wait a minute, Mr. Simon, the limit, you could actually give an answer here. Sure, you can. Because from the left and the right, the square is going to get rid of any negatives. Do your patterns. You'll notice that we could actually say infinity as an answer here, because it's a limit by the arguments that we made before. But I also warned you about this. I can use infinity as an answer to a limit, but I can't use it to describe any other kind of measurement. That's a no-go in all math. You don't use infinity as a final answer to some sort of measurement. So I can't say that the slope is infinite. I can't say that the derivative is infinite. I can say the derivative is going to infinity as x goes to 0, right? Because then that's pattern-based, that's limit language, right? But the derivative itself is undefined. Right? We cannot take a derivative at this point. It is an infinite pattern. Okay? So I hope that this has helped you understand what a derivative is and helped you get the idea of what you need to go and practice to compute a derivative function and also finding equations of tangent lines. Next lecture, we find a way to make this whole process more efficient.
First, that absolute value of x, the v shape, right? You can see the cusp there at x equals 0. Very sharp 90-degree corner here. And we say that the derivative doesn't exist there. And it was very blatant on this one. You can tell the slope is -1 on one side all the way up to the point. And it's +1 on the other side all the way up to the point. So there's no way that the limit from the left and the right agree. Let's see what happens when I do the derivative of that function. Okay, look, it actually gives me the derivative function. You can tell it's saying that the derivative is -1 on this whole side and +1 on this whole side. The derivative is a slope, remember, and I'm measuring the slope of these two straight pieces. So it's -1 the whole way here, +1 the whole way here. So I've actually got a break here. The derivative doesn't exist at 0 because it skips from -1 up to 1. It just jumps, and it can't be defined at either location. Now, I in passing mentioned x to the 2/3, just so that you could see the shape. It comes all the way down, kind of like a square root function, right? More like a cube root. And then it hits this sharp cusp corner right here, and then it extends back out. It would definitely be undefined there. And there's more even of an infinite nature on that one. But the fact that it's different from different sides, right? There's a cusp, no derivative there. And then x to the 3/5. you can notice right here in the middle, right here, it gets vertically lined up right there. Just at this one point, the tangent line would be completely vertical, and we would have a problem with the derivative being something that would go off to infinity at that point. So we wouldn't have a derivative at that point. Watch what happens when I try to take the derivative of that one there. Let's do the same thing again. Derivative function a of x. Look at what happens. This is the derivative function for that right here. See, it has this infinite middle piece right here. It's actually an asymptote, and it's just hugging it really, really tightly right here. It's completely not defined. Look at the division by 0 that would happen in the derivative function, right? This derivative is very, very not defined at x equals 0.